Okay. Hi everyone. My name is Raymond, and so today the plan is to work through the three problems from USACO Silver, um, and this was the contest in December of last year. So let me see if I can share my screen. Okay. All right. So before I start, if you guys have any questions at any point, please feel free to stop me. You can just unmute or send something in the chat. I'll try to watch for all of that. Okay, and then I got these solutions from the official explanations that USACO posts. So the solution here should be the same as what they have. I just hope that one thing really hate about the USACO solutions is they never include any pictures. So I hope that my slides could help a little bit to digest the solutions and make it a little bit more intuitive. Okay, so I'm not sure if everyone has already seen the problem. So here's the gist of problem one. So we have these K grass patches in a line, and this is just a number line. So each grass patch is represented by an integer position on this line. And we also have M cows from Farmer Nodge, the nemesis of Farmer John. So Farmer Nodge has M cows also placed on the same line. And now Farmer John needs to choose locations for his N cows. And after he does that, we for each grass patch, the cow that is closest to that patch claims it. So what we want to do is to carefully choose the locations for Farmer John's cows to maximize this value. So this value is determined by what patches you control, you claim, and each patch is given a particular value in the input along with the location. And then after you decide how you want to place Farmer John's cows, the closest cow to each grass patch claims that particular patch. And if Farmer John claims it, then he gets that amount of value that's associated with the patch. So let's look at the sample input and what this actually looks like. So here we have this number line and 6 patches of grass. And the number on top of each, let me see if I can, can you guys see my mouse at all? I'm not sure. Let me just try to keep going for now. So the number on top of each grass patch is the value associated with that patch. So here the leftmost patch has value 4, and then some of the rightmost patches have some of the highest values. And then Farmer Nodge's cows are what these red pentagons are. So right now there's 5 of these cows. All of them are Farmer Nodge's. So what we want to do is to put down N more cows that belongs to Farmer John. So all of this stuff on the picture is given to us in the input. So we know how many grass patches there are, where each each of them are and the value for each of them. And we also know how many and exactly where Farmer Nodge's cows are. And finally, we're also given a number, the number n, which is how many cows we're supposed to put down for Farmer John. So in this sample input, we're supposed to put down 2 cows. And so this turns out to be the optimal output. So we can get a total value of 36 by putting down 2 cows where these arrows are. So first we can, if we look at the arrow on the right, this arrow is closer to both of the patches at the very right than any of Farmer Nodge's cows. So we can claim those 2 patches on the right. And then the other arrow on the left, it's directly on top of this patch with value 10. And so we sort of automatically claim it because Farmer Nodge can't be any closer than that. So I think this is the optimal solution for this sample input. By using 2 cows, we can get 36 points. And in our output, we only need to include what's the maximum amount of value that we can get. We don't need to specify how we're going to get it. So for this output, we don't need to say where the cows are. We just need to say the maximum value is 36. Okay, so let's try to think how we can maximize this value. So if we happen to have at least k cows, where k is how many grass patches there are, then our job is really easy. We can just put a cow on top of each of the grass patches, and that would automatically claim us all of them. And so we can get all of the value. So that's one case. If we have, turns out we don't need k cows to claim all the patches. If we just have 2 m cows, so if we have double the amount of cows that Farmer Nodge has, then we can also claim all the patches. So what we can do is for every cow belonging to Farmer Nodge, we can sort of put 2 cows right next to it. And we put them really, really close so that it's the Farmer Nodge's cow is kind of sandwiched in between. And then this way we'll be closer than them to all the patches. If we look at this picture here, if we just do that, put 2 cows right next to every one of Farmer Nodge's cows, then we're closer to all the patches. So if we only have 2 m cows, we can still claim all the patches. Okay, so that gives us some ideas. So first of all, the m cows belonging to Farmer Nodge, they divide the number line into m+1 segments, right? So back here, when they had 2 cows, we have 3 segments. And then for each segment, we can claim all the patches in that segment using just 2 cows. So this is sort of another way to look at sandwiching Farmer Nodge's cows. Instead of putting 2 cows around every cow, what we can do is for every segment, put 2 cows at the very end, but closer than Farmer Nodge's cows. So it's still what this picture is showing, just phrased a little bit differently. And also, there's sort of an edge case where for the 2 segments at the end, at the very left and at the very right, we only need 1 cow instead of 2 cows to get all the points. Okay, so So we know that for each of these segments, we can claim all the patches using just 2 cows. And if we can somehow figure out how many points we can claim using just 1 cow, then what we can do is we can go through each of these segments and then calculate what our payoff would be using 1 cow as well as using 2 cows. And then if we have those numbers, then we can determine what our maximum payoff is using n cows. And so how we do that, let me show an example. So here we have 4 cows from Farmer Notch, so 5 segments. So at the very left, the first segment, it's only 1 patch of grass, and because this is a segment at the end, we only need 1 cow to claim all the patches. So using just 1 cow, we can get a value of 4. And then for this second segment here, turns out we can also just use 1 cow to get the whole value because there's only 1 patch. So we can put our cow directly on top of the patch and we'll get 6 points. Next segment has no grass, so we can skip it. And then this 4th segment is the most interesting one. So here there are 3 patches. And if we use 2 cows, if we put 1 cow at each end of the segment, then we can get all the points, which is 22 points. But if we only use 1 cow, I think we can only get 12 points, which is the 2 patches on the right side. If we put our cow somewhere to the left, then we'll miss both of the patches on the right. So here, the maximum 1 cow payoff is just 12. So once we have these numbers, what we're trying to do is figure out what will our total payoff be if we have n cows. So we can sort this list and sort of just choose the n highest. And because we have two cow payoffs here, we have to sort of modify this list a little bit. Instead of writing 2 cow payoffs as just an we need to rewrite the 2 cow payoffs as like sort of how many bonus points we can get if we put in 2 cows instead of 1 cow. So if we go back 1 slide, here instead of writing the payoff as 22 for the 2 cow, we can write it as 10 because 22 minus 12, that's how many extra points we will be able to get by adding another cow in that interval. So for this example, the list would be 4, 6, 10, and 12. So each of those numbers correspond to putting down 1 cow. Okay, so we can sort those numbers and then just choose the n highest, and that would be our total payoff. Okay, so this is an overview of what we have so far. So for each of the n+1 segments on the line, we can calculate the payoff we would get by using 1 cow and 2 cows. We put the payoffs in a list, and we have to rewrite these 2 cow payoffs as the difference between the 2 cow and the 1 cow payoffs. And then we sort this list and just pick the highest n numbers, add them up, and that is our final answer. So now what we have left to do is how we can calculate these 1 and 2 cow payoffs. So 2 cow payoffs are easy. With 2 cows, we can get all the patches. So we just need to add up the values of all the patches in that interval, and we're done. So that's the easy one to do. And then for 1 cal payoffs, here's a picture of what it would look like. So if this yellow arrow is where we put our cal, then on the right side, we get to claim half of the space between ourselves and Farmer Nodge's cal, right? Because the half that's closer to us, well, it's closer to us, so we get to claim that half. The other half is closer to Farmer Nodge, so they claim that. So we claim half of this space on the right, and likewise on the left, we also claim half the space. So actually, in total, we claim half of the total space as well. So whatever, no matter where we put our cal in this interval, in the end, we end up with half of the space in this interval. And so we can use that information to calculate this 1 cal payoff. So this payoff ends up being the maximum sliding window sum of in this interval. So we first find out, so first the window size is half of this segment, and then we slide this window along and find out what's the maximum sum we can get inside this sliding window. So here it looks like it would be 16. I don't think the 10, 4, and 8 would all fit inside this window. Okay, so that's, oh yeah, okay, so that's the idea for this one. I can show you my code really quickly. Okay. Okay, so here, we'll start with the main function. So here we're just reading in inputs. Here we're sorting everything. So the inputs include both the grass patches and Farmer Nodge's cows, and we can sort them together. And then we look at each segment. We calculate what would be the 2 cal payoff, and then if we're not at the end segments and if we're not at the end, we also calculate the 1 cal payoff, which is this max sliding window sum, and then we put those in a list. And then at the end, we sort this list and pick out the end highest things. And specifically how we do this sliding window sum is, so X is a list of grass patches in this segment, and then so start and end is where the segment, the boundaries, and then width is our width is the total width of this window. So essentially what we're doing is just going one patch at a time, and we keep a sum variable, and we update it every time we move it. Okay, so let me go back to the slides. I think I'll just stay out of presentation mode because I think we lose the mouse when I go in. So I'll just do this. Okay. This next problem, we have n fields also on a line, and m paths among these fields. So this is a graph problem, and we want to connect the left and rightmost fields. So these fields are numbered 1 through n, so we want to connect field 1 to field n. And on top of the m paths that are already given to us, we can only build at most 2 paths. And we can build a path between any pair of vertices, but it's going to cost us I minus j squared. So if I'm connecting vertex I and vertex j, it's the distance between them squared. So paths that are sort of shorter are cheaper. Paths that are connecting vertices further away are more expensive. Okay, so here is one of the sample inputs. We have 5 vertices, and there are 2 existing paths. So these 2 paths are already there, and we're trying to connect the first vertex to the very last vertex. And here we have maybe 2 reasonable options. So one option is to just build one path from this vertex here and connect it directly to this vertex here. The other option is to build 2 paths from here to here and then from here to here. And so for this one, turns out that second option is better because each of those only costs 1 because we're only doing step hops, and then the other option would have costed 2 squared, should be 4. And okay, so here's another example. So we have 3 paths already built for us, and again we're trying to connect the first vertex to the last vertex. So here what we can do is we build connect these 2, which cost 4, and then connect these 2, which cost 1, and then we'll have this path with a bit of a loop, but ultimately it connects us to the last vertex. So here our total cost would be 5. Okay, so our first step, we can start by finding the connected components of each of these vertices. So here, these two vertices are already connected. So this is one component. This vertex is on its own. These 2 blue ones are connected together, and these 2 red ones are connected together. So this is the same graph as the one we used on the last slide. And so essentially what we're trying to do is connecting the green component with this red component. And sorry about this line here. I just realized now that it kind of looks like there are edges connecting everything, but it's just there to sort of show, like, have some notion of the distance between the vertices. Okay, so now after we find the components, we have several cases. The easiest case is if fields 1 and n are already connected. If they're already in the same component, then we're done. There's nothing to do, and our cost is 0. So the next case, or rather, if that's not the case, then we have 2 options. We can either use one path. We build one edge to directly connect the green and the red components. This is what is being shown here. One example of this is if there's some point where a green vertex is just one step away from a red vertex, then building one edge is the best we can do. So as our first option, we can directly connect the green and the red components using a single edge, or sorry, this should say option 2. Our other option is to connect through a third component. So here, to connect the green to the red, we're sort of routing through this blue component. So we connect the green to the blue, and then somewhere else we connect the blue to the red. Okay, so another way to visualize this is that on the left side, we have the green component where we're starting. On the right, we have the red one where we're trying to go. And in the middle, there's a bunch of other components, right? In the actual input, these components could be overlapping a lot. So not necessarily, like for example, here we have this vertex, this red vertex that's actually on the left side of this green vertex. So they're not disjoint, they could be overlapping, but this is the general picture. So we have a bunch of components that we can route through essentially. So here are all of our options. So this edge at the bottom, this is our first option, which is to directly connect the green and the red components. And then each of these other pairs of edges, they represent routing through an intermediate component. So we can go through maybe this light blue component and draw an edge into it and another edge out of it. Okay, so those are all of our options. So what we have so far is to, we can first run DFS to find these connected components. And then, so here we're using start to denote the component number of the first field. So this is the green component, and is the red component. And then we can loop over every single possible intermediate component and then find what would be the cost of connecting the green to that component, to that intermediate component, and then plus the cost of routing from that component to the red component. So if we loop over every single possible intermediate component and find what would be the cost of going through there, then we can simply pick the smallest one, and that will be our answer. Or well, we also have to consider this like sort of one, the direct path, but the minimum of all of these options would be our answer. So we need somehow to need a function to compute what is the distance or what is the cost of connecting two components together. So to do that, we can first try to find how we would compute the distance between a single vertex and a component instead of a component to a component. So this is slightly easier. For example, if we're trying to find how we can connect this one purple vertex to this red component, then we sort of have two ways we could go. We could either connect with the closest right vertex on the right or the left, right? Any other red vertices that are farther away are not really worth considering. We only need to choose between the two that are immediately or that are closest to this vertex. So what we can do is, if we have a sorted list of vertices in this red component that we're trying to connect to, then we can use binary search to find what are these closest to vertices in the red component. And then we find how much it would cost to connect to each of them, and then we just choose the less expensive one. Okay. So we now know how to find the distance between a single vertex and the component. And thankfully, it's not super tough to generalize that to connecting a component with a component. What we can do is just loop over all the vertices in one of the components, find the distance to the other component, and then take the minimum of everything we found. So here's a visualization of that. So to find the distance between this dark blue component and say the red component, we can do is loop through every single vertex in this component. We find the distance between this vertex and the red. And then after we find that for all the vertices, we just choose the closest one. So let's say this vertex has the smallest distance to the red component, then overall the distance of the blue component is just that minimum distance. Okay, so to recap, we first find these connected components, then these are our options. We loop through each possible intermediate component, and then find the distance of that component to the red, plus that the distance from that component to the green, and then we choose the one that's the least expensive. Okay, so let me pull up my code for this one. Okay, so we start, this is just reading input stuff. Then we run DFS to find the components. And then for each component, we also keep a list of vertices that are in that component. That's this neighborhood vector here. And then for each component, we sort that vector because we need to do binary search on that vector. So we sort the list of vertices in every component in increasing order. And then we loop through every single possible intermediate component. And we compute this cost. So this is the distance, the cost of connecting the green component, the starting component, with this intermediate component. And this is the cost of connecting the other way from the red to this intermediate component. And then we just take the minimum of all of those, and that's the answer. So for this distance function, what we do is loop through every single vertex in this component, and then run binary search, and then that gives us the two closest the closest vertex in the target component on either side of this vertex, and then we take the closer one, and then our final distance is the minimum of all these in the loop. Okay. And okay, so this is our final problem. But before I go on, does anyone have any questions so far? Okay, so for problem 3, we're given n intervals. Each interval is represented by a starting point, and an ending point. So S, Si, Fi. And both of these numbers are in the range from 0 to m. So all of these intervals live in this big interval 0 to m. So there are a bunch of these intervals inside this big interval. And then what we want to do is for every k in 0 to 2m, we want to count the number of ways to pick two intervals, I and j, so that when you add the starting points of those two intervals together and add the two ending points of those intervals, k is in between those two sums. I think it's easier to see what's going on with this problem just with a drawing. So this is the sample input. So the m in the sample input is 5. So everything lives between 0 and 5. And we have two intervals up here. So one of these intervals is from 1 to 3, and the other is from 2 to 5. Okay. So what will be our output? How will we compute that? So the output, we're counting pairs of intervals, right? Number of ways we can pick two intervals, I and j. So we can start by listing out all the pairs. So in this problem, we can pick repeats. So we can pick the same interval twice. So we can have the interval from 1 to 3 twice. We can have the interval from 1 to 3, and then the interval from 2 to 5. We can have the other way around, the interval from 2 to 5, and then 1 to 3. And then we can have two 2 to 5s. The way we can visualize this is this graph. So this first one here represents picking two 1 to 3s. So if we look back here, if we add up the starting coordinate, 1 plus 1 is 2. So that's why this starts at 2 here. And then if we add up the ending coordinates, that gives us 6. So this ends at 6. And then these are the two that are the same. They correspond to 1, 3, and 2, 5. So 1 plus 2 is 3. 3 plus 5 is 8. So this starts at 3 and ends at 8. And then the last one is 2, 5, 2, 5. So that starts at 2 plus 2, 4, and ends at 5 plus 5, 10. Okay, so the output at every coordinate k is sort of how many of these layers are there at k. So for example, at k equals 3, the output would be 2, because there are two, it would be 3 because there are 1, 2, 3 layers at k equals 3. At k equals 2, it will be just 1. And at k equals 5, it will be 4. So we can call that like the ply of k, how many layers are there at k. And also one more detail is that when I graphed these intervals, I used the white solid line, and then here I'm using the gray sort of chalky kind of line to show that these aren't the intervals in the input. These are sort of what you get when you add two intervals together. So these are pairs of intervals. These white lines are the intervals themselves. So here we have so we have two intervals. So we have 4 possible pairs of intervals. And our answer is how many pairs there are at that number, how many layers. Okay, so for our first step, we can run a nested for loop, two for loops, and sort of just generate all of these possible pairs, right? So for this, we can do like for I less than 2, for j less than 2, and that would give us all 4 of these pairs, possible pairs. And then we need some way to find this ply of k, how many layers there are at k. And one way to do that is to keep track of how many pairs start and end at each value of k. So let's see what I mean by that. So here at the value of k equals 2, oh, okay, sorry. These should be like the gray chalky kind of line. This is these are pairs. So at the value of 2, we have one pair starting at this coordinate. So we write down we have one pair starting here and no pairs ending here. At the value of 3, we have 2 pairs starting. So we write that down. At the value of 4, we have just one pair starting. At 5, we have nothing going on. At 6, there's one pair ending. 7, there's nothing. And 8, there's 2 pairs ending. 9, nothing. 10's one pair ending. So for every coordinate, we write down how many pairs are starting at that coordinate and how many pairs are ending at that coordinate. And then what we could do is we sort of scan this number line from left to right. So here I've switched these starting and ending numbers to just be like +1, +2, +1, and so on. And then so we keep a cumulative counter of how many layers we have. So initially the counter is 0. We don't have any layers in this region. And then we hit the number 2. And we see that there's a new pair or new layer starting at 2. So we increment our cumulative counter to say now we have one pair, one layer. And then we go on to the next coordinate. Here we have a +2, so 2 new layers are starting at this coordinate. So we need to update our counter to 3. So we increased it by 2. And then at the next coordinate, there's one more layer starting. So now the counter is 4. The next coordinate has nothing going on. The next coordinate has one pair ending, right? But I put these ending numbers sort of shifted a little to the right because when we were at that coordinate where the pair ends, that doesn't affect how many layers there are at that point. So here, even though one pair is ending at 6, we still have 4 layers. It's only after this coordinate that we decrease our layer by 1. So that's why it's shifted a little to the right. So we don't change our number immediately, but after we're done with this coordinate, we subtract 1. So we're this layer is gone after 6. So at 6 we're 4, and then at 7 that layer is gone. So we're at 3 layers, and then at 8 we have 2 layers ending. But at 8 we still have 3, but after 8 we lose 2 of them. So at 9 there's only 1. At 10 there's only 1, and we lose that last one as well. Okay, so this is what our answer would be. The problem That's exactly what the problem is asking us to do. So for every k between 0 and 2m, count how many intervals, how many pairs of intervals you can pick. And that's what we wrote down here. So between 0 and 2m, we have a number representing how many pairs there are at that coordinate. Okay, so here's what we have so far. We loop over every possible pair of intervals. And then we write down how many pairs start and end at each coordinate, at each value of k. And then we start by setting answer to 0. This is our cumulative counter. And then we scan over this 0 to 2m, this number line. And then, so for each value, we first add we add however many pairs start at that coordinate. We output our answer, and then we subtract however many pairs are ending at that coordinate. So that's what we did on this slide. At each coordinate, we first add this number, then we write down our answer, and then if there's if we need to subtract, we do that after we wrote down our answer. So this is sort of the 3 steps that we need to do. Okay. So there's one problem with what we have here, which is the first loop, which runs over every possible pair. This would be order n squared. And n could be as high as 200,000, so that would be a problem. However, m is only 5,000 at most. So one way to address this is, instead of storing the intervals themselves, we can instead store sort of how many intervals start and end at each point. So this sounds a lot like what we did before with this, but to clarify, this is how many pairs. So this is after we add 2 intervals together, how many pairs start and end at each point. What we're doing here is, in addition to doing that, we'll also just store how many intervals start and end at each point, instead of storing the intervals themselves. So here's an example of that. Let's say that we have these 5 intervals, and so here we would write down that we have 3 intervals starting at 1. This is pretend that there's another interval starting here. I wanted to say that there were 2 intervals starting at 3, but this is actually an ending interval. So pretend that there's another interval starting at 3. So if we have 3 intervals starting at 1 and 2 intervals starting at 3, then that means there are 6 total pairs of intervals, or that contributes 6 pairs of intervals starting at 1 plus 3. Because what we want to do with these intervals is we go through pairs of them, and then we add their starting coordinates up and we add their ending coordinates up. So if we instead of storing coordinates themselves, intervals themselves, if we store how many intervals are starting and ending at each of these coordinates, then this is what we could do. We could, for every pair of starting coordinate, if we add them up, there would be like 3 times 2, however many, let's say there's a interval starting with this first coordinate and B interval starting with the second coordinate, then that contributes A times B pairs to A times B pairs that start at the sum of the starting points. So the point of doing that is that instead of looping through every pair of intervals now, we can loop through every pair of starting points and ending points. And because all the starting points and ending points are in the range 0 to m, and m is only 5,000, m squared is okay, while n squared is not. So this might be easier to digest by just looking at the code. So let me pull that up. Okay, so code for this one is a lot shorter than the other ones. So the most important variables are these four. So we have interval start, interval end, and pair start, pair end. So these two represent how many intervals start and end at each coordinate, and then these two represent how many pairs of intervals start at each coordinate. So that's why this is twice as long as this one, because when you form the pairs, you're adding two intervals together. So the range becomes twice as big. Okay, so this is what we do. We're reading in inputs, and then each interval, we have the starting point A and the ending point B. So once we read that, we increment interval start A. So this is how many intervals start at coordinate A. And then this is how many intervals end at coordinate B. So we, every time we read in an interval, we increment those two coordinates. And then we loop through, this is our m squared loop. So for every pair of starting coordinates, I and j, we increase this pair start of I plus j by how many intervals start at I times how many intervals start at j. So if we have x intervals starting at I, y intervals starting at j, then that we can pair those up, we can have x times y pairs out of those. And each of those pairs would start at I plus j, right? Because we have one interval starting at I, one interval starting at j. So if we pair them up, the sum is going to be I plus j. So that's why we increase pair start I plus j by this. So this is how many pairs start at I plus j. And then we do the exact same thing for pair end. This is how many pairs end at coordinate I plus j. And then, so after that m squared loop, we would have this information for every single coordinate. And then now we just need to calculate like the ply, how many layers are at each coordinate. So we scan through the line from 0 to 2m, and then this is the three-step process. So we add how many pairs start at I, we output, and then we subtract how many pairs end at I, and that's it. Okay, so any questions about this third problem or anything before? Okay, then that's everything I have planned. Uh, thank you everyone.